All right, well, welcome to solving nonlinear systems. So we spent a bunch of days looking at what happens when we're graphing two lines or three lines in a three-dimensional plane and how to solve those systems. But now we're going to look at equations that are not linear. So I wanted to give you a visual idea of what's happening here. So instead of graphing two lines on a grid, now we're going to see like a line and a parabola, like a quadratic, or a line and a circle. We remember we learned about equations of circles. Remember circles, their equation looked like x squared plus y squared equals r squared, that sort of thing. So we might see an equation that looks like this with a linear equation, or maybe a circle and a parabola and all that. And what we're looking at, just the same as when we were solving linear systems, is where they intersect. So wherever the two functions intersect, those are going to be our solutions. And one of the first things you should be seeing is that we have multiple intersection points now when we're looking at non-linear systems. So the first two had two solutions. This one has two, but over here you see we can have a lot of solutions depending on what types of functions we're graphing and where they are. So be prepared as we're working. We're going to be seeing equations that have some squares in them, and we're going to be seeing some multiple solution systems. But in the same way as we saw with linear, we also might see some nonlinear systems that have no solution, right? So like a parabola that opens up and a line below it. These two functions will never intersect, and so we'll still have some no solution where we will write inconsistent. If we see something algebraically that just doesn't make sense. So visually, this is what's going on. Let's just jump in and take a look at what's going on algebraically. So what I want you guys to do is just listen first, watch how I'm kind of walking you through, and then you can pause and copy this all down, okay? So the original, the system that I'm giving you here is a quadratic and then a linear, right? So visually we have a parabola and then a line. We're not sure exactly how they intersect yet or if they intersect at all, but we should be thinking about these two graphs on the coordinate grid. We want to try to line up the x's, the y's, the equal signs, the constants just in the same way, but notice that these are not like terms, right? So when we combine, we're going to have to keep them separate. In this equation in particular, the y's end up canceling without us doing anything, which is really nice. So the y's add to 0. And so when we combine these vertically, 4 plus 2 is 6. But when we add the x squared plus the x, notice we have to keep them separate because they're not like terms. Again, the y's canceled. So what we see is that very quickly, this system becomes a quadratic. So we're going to have to solve our quadratic. So remember, we spent a lot of time first semester looking at that. To solve a quadratic, the first thing we need to do is set the equation equal to 0. So we're going to subtract 6 over. Then two numbers that multiply to negative 6 and add to 1 are 3 and negative 2. We'll use the zero product property to set these individual factors equal to 0, and we get two values for x. So what this means is we could possibly have two intersection points. So if we look up here, it looks like maybe this parabola and line system might look like this. So we need to find those 2 points where this parabola and this line are going to intersect. And so we just did half the problem because we found the two x values of the two different points. So now when we circle back and go to plug it into the original equations, again, we can plug it into either equation, right? We can plug those x values into either equation, but we're going to have to plug in negative 3 into one and then also 2 in for x. So this brings us to the second part of the solving part. So once you get your values for one of the variables, you have to consider both scenarios, when x is negative 3 and when x is positive 2. And so we're going to plug it in again into one of the original equations. It doesn't matter which one. In this case, I tend to choose the one that looks a little bit easier. I think linear equations are easier to work with. So I'm going to plug in negative 3 for x and 2 for x into that linear equation and solve. So we get negative 3 minus y equals 2. I'm going to add 3, negative y equals 5, so then y equals negative 5. So when x is -3, y is -5. This is one of my solutions to that system, which is great. I found one of my solutions, one of my intersection points. But now I have to repeat the process, but this time put in 2 for x, and again, go through the algebra, and we get a y value of 0. So we find the 2 intersection points, the x and the y. Okay, so notice we solved with elimination. We ended up having to work with a quadratic to get our 2x values. Then we had to plug both of them back into one of the equations. Again, I chose the linear one. I plugged in -3 for x and 2 for x over here and showed all my work here to get the corresponding y value. Now, as you're working, and if you're thinking of SAT, you guys get to use this online calculator called Desmos, and it's actually really, really helpful with these types of problems. So I wanted to show you this really quickly. If you go onto Desmos, you should have it in self-service. You can click on and type in these equations. So you just type in like x squared plus y equals 4, exactly how you see it, and then do the linear, and it'll graph the 2 equations. And what's really nice is you can get a visual of what's going on. That quadratic is an upside down parabola, and then that line. And if you just tap on the intersection points, you can see the solutions, just what we solved algebraically, -3, -5, and 2, 0, are the points where these 2 functions are intersecting. So Desmos is really nice when you have, when you're like doing your homework, because obviously we can't use it on a quiz or test, but you can check your answers on Desmos for these more complicated nonlinear systems. Okay, so again, go ahead and pause, and at any point you should be pausing the video and copying these things down, but listen first so you can understand. All right, so let's look at this second example here. So here we have an x squared and a y squared, which means this is a circle, and then we have a line. So again, lots of different numbers of solutions. For this one, I see this equation, nothing really can cancel because x squared and x can't cancel, y squared and y can't. So instead of solving by elimination, this one I'm going to solve by substitution. So I'm going to subtract x over and get an expression for y. So that means when I go and take this top equation, I'm going to say x squared plus y squared equals 9. But I put these parentheses because instead of writing y squared, I'm going to put this expression for y right here that we had isolated before. And then remember, whenever you have a binomial squared, you need to FOIL it out. So we're taking the -x plus 3 times -x plus 3. That leaves us with positive x squared minus 6x plus 9. Okay, so then -x times -x is positive x squared, and -x times 3, -x times 3, -6x, and then 3 times 3 is 9. And so then when we go to combine like terms, I can subtract my 9 over and get the 0. X squared plus x squared is 2x squared, and then -6x. So again, I'm left with a quadratic that I have to solve. I set it equal to 0. Now I'm going to factor it by taking out a GCF, the 2x. So 2x squared divided by 2x is x. -6x divided by 2x is -3. And then we can use the 0 product property. 2x equals 0, x is 0. X minus 3 equals 0, so x is positive 3. So again, we have 2 x values, which means we could possibly have 2 intersection points. So we need to figure out the corresponding y value for both of these guys. So we are going to circle back. We are going to plug this back into one of the original equations. I'm going to choose this guy because it's already isolated for y. But I have to plug in 0 for x and 3 for x. So this is going to take some time. So this is when I move over and I say, okay, well, what's going to happen when x is 0? Well, when I plug in 0, I get that y is 3. So I get my coordinate point when x is 0, y is 3. This is one of my solutions. But then I also need to figure out, well, what happens when x is 3? So when x is 3, I'll plug it in. -3 plus 3 is 0. So then I have my other intersection point when x is 3, y is 0. So I can solve the system using substitution. Again, it requires a ton of algebra, and we're going to be solving quadratics a lot. Once you get your 2 values, you have to look at both scenarios, when x is 0 and when x is 3. and plug both of those values into one of the original equations. All right, let's keep moving right along. So here we have our third example. This one's really nice because, again, it's lined up nicely, and both of these are x squared, both of these are y squared. So we can really treat it like a normal system. The y squareds end up canceling on their own without having to do anything. So when I combine my like terms here, 1x squared plus 2x squared is 3x squared. This is 0. Equals 27. So now I can go through and solve for x here. So I'm going to divide both sides by 3. X squared equals 9. Here I'm going to take the square root of both sides, and we get that x equals positive or negative 3. So here, again, we see two values for x. So we have to consider both of them. We have to consider when x is positive 3 and when x is negative 3. So when we circle back, we can plug it into either one of the original equations, right? We can take x and plug it into either one of the originals to get y. I'm choosing this top one. So I'm going to take x squared plus y squared equals 10. I just copied over, but I put parentheses around where x should be. And in this first scenario, I'm going to look at what happens when x is positive 3. So I get 9 plus y squared equals 10. Subtract the 9. I'll take the square root of both sides, and I get y equals plus or minus 1. So I want to pair x with both positive 1 and negative 1. You can write it as a joint coordinate, or you can write it separately if you want. You can say 3 comma 1 and 3 comma negative 1 is fine, because when x is positive 3, it's paired with a positive 1 and a negative 1. So we do the same thing, but now we have to consider when x is negative 3. So over here we see very similar work, because when you square negative 3, you get positive 9 as well. So the work ends up being exactly the same over here. And then we pair negative 3 again with plus or minus 1. So we're really utilizing all of our algebra skills that we've learned throughout the years. Okay, awesome. Let's keep going. So we're going to see some like special cases, as always, as far as like no solutions, but also some trickier sort of nonlinears. And this is the first one with a square root. So here, when you have the square root, our only option is to solve by substitution. So notice, since the y is isolated, I'm going to plug this expression in for where I see y here. And so as I rewrite this top equation, x squared plus y squared equals 19. I put parentheses around where y squared is, and inside I'm going to put the x minus 1. Okay, so I'm going to solve by substitution, substituting this expression in for y right here. Now what's really nice is this expression is being squared. So when you square a square root, they undo each other. So this is going to undo, and I'm just going to, the x minus 1 is going to get to come out. And now I have a much nicer quadratic that I can solve. When you go through the steps of solving a quadratic, you're going to subtract 19 over to set it equal to 0. Then you have this quadratic here. So what two numbers multiply to negative 20 add to positive 1? That's 5 and negative 4. The zero product property tells us that x is negative 5 and positive 4. So we solved by substitution, and we got our two x values. Now, with square root functions, we have to consider that when you take the square root, you can only take the square root of 0 or positive numbers, right? So this one is a little bit of, this one is like the pickier of the two nonlinear equations. So when you have a square root, once you solve for x, you have to plug it back into the square root equation. So we're going to go here over to the side. We must plug it into the square root equation. We have to see what's going on when x is negative 5 first. So we'll plug in negative 5. And we see that, wait a second, we can't take the square root of negative 6. So x can't be negative 5 because it won't intersect with that square root. So that's fine, that we're not going to have a solution at negative 5. So let's figure out what happens when x is 4. Our other solution from the quadratic, when we plug in 4, we get that y is the square root of 3. Notice it's not the plus or minus value because we didn't have to take, this wasn't y squared first, then we had to take the square root to solve, right? It just said y equals the positive square root of that guy. So we just pair 4 with root 3, and that's our only solution. Okay, so again, when you have a square root in your system, you can solve by substitution. Once you get your values for your first variable, make sure you plug them back into the square root equation to get the partner, because you might end up with one of your x values not actually being a solution. And you'll only know that it's not going to work out if you plug it into the square root function. Okay? All right, we're on to our last example for today, and that's when our system has this like XY term. Okay, so this is something brand new. We have never talked about what this type of function looks like. Don't worry about what it looks like on the graph. Just know that when you see a system with an XY term, this is the term that you want to eliminate no matter what. So I know that we could eliminate the x squareds, but we want to be, if we eliminate the x squareds, we're left with an equation with two variables, and then we would be stuck. So when you see this xy term, we want to eliminate that guy first. So since this is a negative 3xy, we want to make this a positive 3xy. So we're going to multiply this top equation by 3. So when we do that, we get 3x squared plus 3xy equals 45. Remember to distribute it to every term. The second equation, I'm going to copy down exactly as is. And then we're going to see the xy term cancels like we planned. So we do that, and then let's see what's left over. So 3x squared minus 2x squared is 1x squared equals 45 minus 20 is 25. We're going to take the square root of both sides because we are taking the square root in order to solve. That's why we have the plus or minus. So we get x is going to be positive or negative 5. Okay, so then when we move over, when x is positive 5, we have to test that out. So we're going to plug in 5 here and here. So we have 25 plus 5y equals 15. Oh yeah, I plugged it into the original one right here. X squared plus xy equals 15. So then we'll solve. We get 5y equals negative 10. So then y equals negative 2. Oops, sorry about that. I think I copied that over incorrectly. Make a quick adjustment there. All right, so then we get 5 comma negative 2 is one solution. And then we'll do the same thing over here for when x is negative 5. So when we plug a negative 5 in here, we can see that we're going to get negative 5 squared is still positive 25, but this is going to be negative 5y equals 15. So negative 5y equals negative 10, so then y equals positive 2. So we have negative 5 comma positive 2 as our second solution. Okay, so hopefully you see that there's this like nice little flow, right? We're definitely going to have some quadratics that we're going to have to factor or solve using the square root method, solve the quadratic using basic factoring, again, a square root method. Here we solve the quadratic by taking out a GCF. So we're definitely relying on our algebra skills. But then once you get your two values, then we have to consider when x is both of them individually, right? So we have to consider the first scenario when x is the first x value, plug it in, and then the second scenario with the other x value, and then you'll get your multiple solutions. And then again, if you're working on your homework and you have access to your iPad, definitely take advantage of Desmos. You can type all of these in and then confirm that you're getting your answers correct. Or you could also do this by hand. Remember, if you plug in 0 for x and 3 for y, 0 for x and 3 for y, you should satisfy both equations, right? So that's a nice way to be able to check your work as well. All right, guys, I hope this makes sense. Come to class with questions. We'll see you later.